Mars was supposed to be a dead, dusty world until China's Jurong rover uncovered something no one expected. Radar evidence of what looks like an ancient shoreline buried deep beneath the red surface. If this is real, the rules of Mars science just changed overnight. Did China just break open the greatest Mars mystery of our time? And if so, what else have we been missing about life beyond Earth? The answer begins with a mission that challenged everything the world thought it understood about exploring the Red Planet. On July 23, 2020, a Long March 5 rocket thundered off the pad at Wenchang, carrying a payload unlike any China had ever launched. Packed inside was not just an orbiter, but a lander and a rover, 3 spacecraft stacked together aiming for Mars in a single all-or-nothing shot. The mission's name, Tianwen-1, means questions to heaven, echoing a centuries-old poem about mysteries beyond Earth. For China's engineers, the stakes were clear. No backup, no second try. Success would make China only the third nation to reach the Martian surface and the first to attempt orbit, landing, and roving on a maiden voyage. The rocket's 5-ton payload arced away from Earth, bound for a 290 million-mile journey. As the boosters fell away, the spacecraft separated and began its cruise, guided by a team determined to prove that China could match and maybe even outpace the world's best. For the mission planners, every calculation counted. If even one system failed, the entire stack would be lost. But the gamble was deliberate. By combining 3 major milestones into one launch, China aimed to leapfrog decades of slow progress and announce itself as a contender in a new era of planetary exploration. As Tianwen-1 left Earth's shadow, it carried not just instruments and experiments, but a national ambition to answer questions that had waited for centuries. On May 15, 2021, just past local dawn, the Tianwen-1 lander sliced into the thin Martian atmosphere at nearly 5 kilometers per second. For 9 minutes, the spacecraft managed everything alone. First, friction with the air built up enough heat to glow the heat shield orange, shedding thousands of degrees in seconds. Then, at a precisely calculated altitude, the lander released a 200-square-meter parachute, tapered disc gap band engineered for the planet's wispy air. The parachute caught, jolting the descent module and slowing it below supersonic speed. Sensors hunted for surface echoes, radar scanning for boulders, slopes, and safe ground. At 1,000 meters, the lander cut loose its back shell and parachute, ignited its 7,500 Newton variable thrust engine, and hovered, searching for a landing spot. Onboard computers processed hazard maps in real time, steering away from craters and rocks. The engine throttled down for the final meters. Touchdown came at 25.066 degrees north, 109.925 degrees east in the southern Utopia Planitia basin. The rover, named Jurong for the ancient god of fire, now stood on Martian soil. Unlike the drama of NASA's 7 Minutes of Terror, China's approach was measured, quiet, and precise. The landing proved that Chinese engineers could master the most unforgiving challenge in robotic planetary exploration, matching the hallmark skill that once set NASA apart. With Jurong's 6 wheels locked, solar panels deployed, and mast raised, China's surface presence on Mars was no longer a dream. The real work, unraveling the planet's hidden history, was about to begin. Jurong's first days on Mars began with careful, deliberate steps. At 240 kilograms, the rover's 6 wheels pressed into the ancient regolith, setting out across the broad expanse of southern Utopia Planitia. Engineers had equipped Jurong with an unusually powerful toolkit for a debut mission: panoramic and multispectral cameras, a surface composition detector, and a ground-penetrating radar system known as Rover. This dual-channel radar, the first of its kind on Mars, could scan as deep as 100 meters below the surface while also resolving fine details in the uppermost layers. As Jurong rolled from its lander, it deployed its mast and began calibrating instruments, running diagnostics on its radar, and measuring the Martian atmosphere. The rover's progress was steady, covering nearly 2 kilometers over the course of its mission. Each meter added a new layer of radar data, building a subsurface map that would soon reveal patterns invisible to cameras alone. With every transmission relayed back to Earth, Jurong's instruments gathered clues about the buried history of this vast plain. The real promise lay underground, where the radar's pulses would soon probe for hidden structures, sediments, layers, and perhaps signs of a vanished world. For now, the rover advanced methodically, its suite of sensors primed to unlock the secrets beneath the dust. Roughly 10 to 35 meters beneath the Martian surface, Jurong's radar began to reveal a pattern no camera could see. The data showed broad, continuous layers, strata that ran for more than a kilometer. Each one tilted at about 14 to 15 degrees, all sloping northward across the ancient basin. These weren't the random, jumbled layers left by meteor impacts or the cross-bedded swirls of wind-blown dunes. Instead, the layers were smooth and uniform, with a gentle, steady rise toward what orbital maps had long hinted could be an ancient shoreline. The radar's dielectric readings told another part of the story. The layers reflected signals like loose sand, not solid rock or buried ice. Their thickness and consistency matched what Earth geologists call prograding wedges, sediment packages built by waves pushing sand toward a rising shore, just like at a beach back home. Over the course of Jurong's traverse, these buried wedges appeared again and again, always aligned in the same direction, always showing the same shallow upward tilt. For the Chinese scientists analyzing the data, the pattern was unmistakable. Here, buried under the Martian dust, was the signature of a shoreline. Layers built by water, preserved for billions of years, now exposed by a rover's radar for the first time. Buried beneath Utopia Planitia, the thickest of Jurong's radar-detected layers reach up to 35 meters. On Earth, deposits of this scale require millions of years of steady wave action. Time enough for a coastline to settle, for tides to rise and fall, for an entire climate system to remain stable. The radar signature points to loose, sandy sediments, not volcanic rock or ancient ice. This is not the aftermath of a sudden flood or a passing storm. These are the fingerprints of a standing ocean, shaped by persistent water and wind under a sky far denser than Mars possesses today. For such an ocean to last, Mars must once have had a thicker atmosphere, enough to keep water liquid, enough to shield a surface from deadly radiation, enough to drive a cycle of evaporation and rain. Climate models suggest that 4 billion years ago, Mars could have worn a pale blue haze above its northern plains, trapping warmth and moisture for millennia. Under those conditions, rivers would have carried nutrients down from the highlands, feeding a shallow sea that stretched beyond the horizon. Astrobiologists around the world now turn their attention to these ancient shorelines. On Earth, the margins of lakes and seas are cradles of evolution, where organic molecules concentrate and the chemistry of life takes root. If Mars ever harbored life, the best evidence may be buried here, locked in the quiet layers beneath a vanished ocean. The stakes reach beyond geology. They touch on the possibility that for a time, Mars was not just habitable but inhabited. The race to bring Mars back to Earth is now a sprint, not a marathon. China's Tianwen-3 mission is locked onto a 2028 launch with plans to land, grab samples, and return them home by 2031. That timeline isn't just ambitious. It's calculated to beat NASA at its own game. NASA's Mars sample return, once the clear favorite, has slipped into uncertainty. Budget fights and shifting designs have pushed the first possible launch to 2030, with samples unlikely to arrive before 2035. The European Space Agency's Earth Return Orbiter, a key piece of NASA's plan, can't even launch until the next decade. Meanwhile, China's engineers are already deep into hardware development, testing a two-launch system, one rocket for the lander and ascent vehicle, another for the orbiter and Earth return capsule. The goal is clear: deliver at least 500 grams of Martian soil and rock, possibly years before the United States. For both teams, the stakes are enormous. Whoever lands those first samples on Earth will shape the next era of planetary science, claim a historic first, and set the tone for future Mars missions. The countdown is on, and the finish line is no longer theoretical. The question hanging over every planning room: who will win the race to bring Mars to Earth? In May 2021, China's Jurong rover became the first non-US robot to operate on Mars, traveling 1.9 kilometers across Utopia Planitia and using ground-penetrating radar to peer 35 meters below the surface. The rover's data revealed layered structures with angles and thickness matching those of ancient terrestrial shorelines, a finding documented in peer-reviewed studies published in 2023. Yet, these signals alone cannot confirm whether Mars once held an ocean. No direct chemical samples have been returned, and the true nature of the sediments remains debated among planetary scientists. As of 2024, both China and NASA are preparing rival sample return missions, with Tianwen-3 aiming for a 2028 launch and a planned Earth return in 2031. Today, Jurong's radar results challenge long-held assumptions and force the global scientific community to re-examine what we know, and what we don't, about Mars' past. Until samples from these buried layers arrive on Earth, the question remains open. Did China just rewrite the story of water and possibly life on Mars?